Okay, welcome to Scaling Instagram Infrastructure. Instagram is a community where people connect with each other through shared experiences in a visual way. A bit of history of Instagram. It was founded in 2010. Less than 2 years later, it was acquired by Facebook. I joined Instagram 3 years ago and have been working on the infrastructure team since then. Fast forward to 2017, we got a new logo, and in the just last 6 months, 100 million new users have joined the community. Since we're talking about scaling today, let's take a look at a typical day on Instagram. 400 million users visit Instagram every day. 4 billion likes are registered. More than 100 million media is uploaded. And our top account has more than 110 million followers. This is across the board 4 times increase in scaling than 3 years ago when I first joined Instagram. Back then, it was a much smaller development team, the app was way simpler, and we have a lot fewer users. But it was fast growing, and we were struggling to keep the service up all the time. One of the common scenes you would see on a Friday afternoon right before the weekend peak time is our on-call engineers who will be staring at the computer screen, looking at the CPU load, and decide whether we need to spin up a few extra web servers for the weekend. Well, we have come a long way since that mode of operation. And so today we're going to talk about in 3 dimensions of growth to enable us to scale to today's level. To scale out is to build an infrastructure that allows us to add more hardware when we need them. And to scale up is to make each of these servers count. And to scale the dev team is to enable a fast-growing engineering team to continue to move fast without breaking things. So first, scale out is the ability to use more servers to match the user growth. From a few servers to quite a few in the data center, to extending to multiple data centers. Instagram was running in AWS from the beginning and continued to do so after almost 2 years with Facebook. About 3 years ago, it moved its service completely inside Facebook data center in order to take advantage of some of the scaling services like monitoring, search, or spam. But as soon as we moved into one of the data centers, Facebook cut out the entire network access to that data center. Why? Facebook takes disaster readiness very seriously. So it would routinely conduct these drills called storms on a regular basis to make sure that all our services can sustain the loss of a region and continue to serve the users in a seamless manner. Instagram architecture at the time was not able to operate in multiple data centers. So we had to play the guerrilla tactic and uproot our whole service to another data center. Unfortunately, disasters are not just theoretical hypotheses. So we needed to get ready for the next time the storm happens or the reality hits. In addition, thanks to our rapid growth, we were quickly running out of capacity in that data center. Facebook had capacity elsewhere, but we couldn't take advantage of that. Power outages and the human errors also contribute to service unreliability. Just a few days ago, a RM-RF type of operation on our container tier was wiping out quite a few of our production servers. Fortunately, we had the ability to move our traffic away from the problem data center. In case you think that this only matters to scalable services such as Instagram, here's a headline from last week, which reminds us even the world's most reliable infrastructure could still have outages at times. And if you don't have another region to fall back on, then this is a suggestion from one of the articles published. I'd say that in addition to praying at the moment of this event, let's put something on the roadmap so the next time we would go business as usual. How do we get there? Let's take a look at the backend stack Instagram had at the time. At the center is the web tier that runs Django with Python. It receives user requests and accesses various backend storage or services for responding to the user. A user request could also trigger some asynchronous tasks that are done in the backend. For example, sending notification to the person whose photos you liked. These tasks are sent to RabbitMQ and Celery for processing. So how do we distribute this stack to different data centers? We identified two categories of servers or services, storage versus computing. Storage servers store global data that needs to be consistent across multiple data centers with replication, perhaps with some latency, but eventual consistency. Computing servers are usually stateless. They process requests by user traffic. The data in these servers are temporary, and they can typically be reconstructed from the global data. Using these two criteria, we now revisit our stack to see what fits where. We use Postgres servers to store user, media, friendship type of data. And a typical deployment in one region is a master with multiple replicas to support high rate of read RPS. The web server would write to the master where data gets replicated, but the reads typically happens on a replica. When going to multiple data centers, it's pretty straightforward with cross-region replication. The Django continues to write to the master, possibly cross-region, but typically only needs to read from a local region. To address the increased latency for writing, we did make modification to minimize the round-trip time for writes by batching requests wherever it's possible. The increased latency between the master and replica turns out to not have been a big problem for us. Next, we use Cassandra to store user feeds, activities, etc. In Cassandra, there's no master. All replicas have the same copy of data with eventual consistency. Consistency can be configured based on application's tolerance for inconsistency, scalability, service availability, and latency. So for example, one application could choose to have write consistency of 2 and read consistency of 1. Going to multi-data center, again, is pretty straightforward. You can have the replicas living in different data center. On the computing side, we grouped Django and Rabbit and Celery into one pod that goes in each region. The global load balancer would send a user request to Django's, but the asynchronous task would be produced and consumed in the same region. That gets us over here, database replication across region and computing resources all contained in one region. But we have left out Memcache. Memcache is a huge part of the scalability story. It is a high-performance key-value store that front-ends the database tier, without which the databases would be crumbling under the read demand. It provides millions of operations per second on each of the servers. Because of such high rate of services, it is very sensitive to network conditions, so latency is a big deal. As such, cross-region read-write is prohibitive. So our architecture decided that we will not provide a global consistent Memcache tier. The work set in the Memcache in each region is determined by user traffic served out of that region. Let's see what problem it might cause. As a user comes in making a comment on the media that gets into, inserted into Postgres server, the Memcache also gets updated by the Django server. Well, another reader comes in, Another user comes in and comes fetch his feed. He's going to use the same memcache tier where the commenter was. So he's going to get the latest comment. No problem when both users are served out of the same region. When we go to 2 different regions, it could be a problem. Since we hash the user request based on a user ID, the 2 people sitting next to each other could be served out of 2 different data centers. Let's see what happens in that case. Again, the user C makes a comment, data gets inserted into the Postgres server. Memcache is updated locally in that region, but it does not update the memcache in the other data center. So even though the comment is replicated in the Postgres server, nobody is invalidating the memcache in the second data center. The user comes in, getting his feed, is going to get a stale comments of the media. Well, it's not a great user experience and could cause a worse consequence than just social awkwardness. So how do we fix the cache inconsistency problem? As user comments comes in, again, we insert into the Postgres database, but we're not going to update the memcache from Django. Instead, we use the Postgres replication mechanism. And we run a daemon on each of the Postgres replicas that tails the database updates. And it then invalidates the memcache in its own local region. Now, when the user R comes in and reads the feed, it's going to be forced to go to Postgres because memcache does not have that entry anymore. Now the user gets the latest comments. While it solves the stale memcache problem, it creates a big load on the Postgres server. Let's see why. This is a picture that has received 1.2 million likes. How do we get this number to display to the user? So we have a table that stores what user liked which media. And we would do a select count star on that table. And this is going to take hundreds of milliseconds to execute. It wasn't a big deal in the past because the like counter was cached in memcache, and every like would just do a memcache increment. So there's rarely any need to go to the database to retrieve this counter. But now, because we invalidate this counter for every like that registers, all these reads after a like would have to be forced to go to the database. So to fix this, we created a denormalized table that stores just the media and the number of likes. Instead of going through a select count star, we just do an index lookup on this table. That reduced the execution time of this query to tens of microseconds, many orders of magnitude faster than the previous query. However, even in this case, the load is still high. You've heard the thundering herd problem in the morning on the Facebook Live problem. This is very similar. When cache is invalidated, there's no such counter in the memcache, then all the Django's coming in would have to go to the database. Even with reduced query time, it's still a lot of load on the database. So we use memcache lease to solve this problem. Here's how it works. The first Django that tries to read from the memcache, instead of doing a normal get, it does a lease get. And memcache returns, instead of a miss, it says, I don't have the data, but you have my permission to go to the database. The second Django comes in within a shorter period of time, does a same lease get, and instead of getting a miss, it's told, I don't have the data, but don't go to the database. I have a stale value for you. You can use it, or you can wait to retry to get the latest data. In most of our application cases, the stale value would be completely valid. So if you get 1 million likes versus 1 million plus 10, for user experience, it's not going to be very different. The first Django then goes to the database, and update the memcache. Subsequent reads would be able to get the most updated value. Now, with these improvements, the database, even though it's still getting higher load than before, it's able to handle the load now. And with the computing building blocks and the replications for Postgres and Cassandra, we were able to build up and extend Instagram into as many data centers as we need to. With that, we now have capability wherever we need it, and service is more reliable, and we're regional failure ready. But we're actually not everywhere. We're mostly in North America right now because the latency from Europe and Asia is still very high. But we also see opportunities there. With the latest features that we have for direct messaging and live streaming, we have identified more and more users with more localized social network, whether it's celebrity, whether it's a group of friends who are in a particular region in Asia. It makes sense to move the data center closer to where users are to reduce this interaction latency. So that would be something that we would like to tackle next. While it is great that we have the ability to add more servers when we need them, we realized we were needing them too fast. While our user growth was healthy, our server growth was far outpacing the user growth. And if we had grown at this pace, since 2 years ago, we would be running 3-4 times the servers that we do now. So I really like this quote from last KubeCon. So when we talk about scale up, we don't mean to buy more expensive hardwares, right, with more CPUs, memories, and stuff like that. Rather, what we mean is to use as few CPU instructions as possible to achieve something, meaning writing good code to reduce the CPU demand on our infrastructure, and to also use as few servers as possible to execute, to carry out those CPU instructions. That's to increase the supply each particular server has. Effectively, each server would be able to serve more users. That's what we call scale up. So let's take a look at the demand side first. We'll go over how we measure the CPU demand, how we analyze where it comes from, and how we optimize where it matters. Let's start with collecting some data. So Linux provides perf event ABI for applications to retrieve CPU instructions for code segments. So we sample user requests and collect these CPU instructions for specific requests, along with tons of metadata, such as what's the endpoint, which data center they're running it from, what kind of hardware they're running it on, so that we can slice and dice on various dimensions. So here's a time series representation of CPU instruction usage by various endpoints. We then implement a set of tools to monitor this metric and alert when it increases above certain threshold. For example, this way. With this jump in the time series representation, we can then match with the event log to see what are the possible causes. Is it a diff that's rolled out? Is it some configuration changes or some backend service rollout? Another very important piece of metadata that we log is whether a specific feature is on or off in a request. This is very critical for us to detect increased CPU instruction demand by a newly added feature whose global impact may not be very easily seen from the previous graph because it's still to a very small audience, but its impact is amplified with this metadata. And with having this data, we add this information right next to the UI where the feature is configured. So when even if the feature is rolled out to 1% or less, in this graph shows more than 8% CPU increase if the feature was rolled out to 100%. So this gives the developer plenty of time to address the regression before it becomes a real problem. This way we make the performance part of the development cycle rather than an afterthought. But we still get innocent looks from developers who say, hey, my div is only one line of log change, can't possibly be causing 20% CPU instruction for a particular endpoint. So now it's time to develop some tools to deep dive into the code base. For that, we use a Python cProfile. cProfile provides performance statistics at function level with code graph information, very much like how Linux perf works. The resulting data can be post-processed and rendered with gprof2dot, which is an open source tool. Using this, you can look at the function and see its overall impact on your code path, the caller-callee relationship, and it helps you focus on where you really want to spend your effort in optimizing. In the past, we already have this, right? This is all open source. Some of our engineers have used these tools to dive into specific performance problems. But the cost of this cProfiling is pretty high. And the process of enabling, disabling is manual, and the prospect of messing with a production server to collect this data is pretty scary for most developers. As our development team grows, this did not scale. So we needed to make the performance data readily available for more developers to access. So we instrumented cProfile collection in our production server continuously. It is a conscious trade-off between cost of collecting this data and the visibility we would gain into our code base. With this instrumentation, at any time, our engineers can just run one command line and generate a call graph like what we saw before. And it greatly improved their productivity when debugging performance issues. While Snapshot was great when looking at the overall picture, but it doesn't help a great deal when you look at regression. So we also put this data in a time series format. So if a caller is making multiple calls to other functions, but you see matching regression in the CPU instruction, you can be pretty sure that, in fact, that 20% regression is caused by the one-line change of logging. So it's time to spend some effort on that. With cProfile running everywhere, we also integrated this data into code browsing that shows how many servers would be needed just to run that function. This is a great reminder for anybody who's looking at our code, the optimization opportunities. So now, let's take a look at some of the optimization we've done with all the visibility we have in the code base. Here's one example. When you load up the Instagram feed, the servers return a number of URLs to the clients. With each URL is the CDN where the client needs to go retrieve the media. This URL generation is based on the media as well as the user, where the user is from, so we can generate the most optimal CDN location for the user. As we started to support a variety of mobile devices with varying capabilities, there was need to generate multiple of these URLs so the devices can choose what's the best user experience they could serve, depending on network condition, the particular device the user has. So we started to give multiple URLs to the mobile devices. The only difference, though, is really the size of the media. But as we were implementing this feature, we were calling the generation of the URL function 4 times rather than once and with just different varying sizes. With the help of cProfile, we understand this is what's happening. So the first thing to do is less. Instead of calling this function 4 times, we call it once and simply overwrite the size function. This is one simple example, but we have numerous such examples with the visibility into the code base. We know exactly what is happening, and we were able to do a lot of these optimizations very quickly. But you might also ask, okay, if the URL generation is so costly, how about we make it less costly? And you would be right. So another major theme of optimization opportunity was that we identify a number of functions that are used extensively, that are pretty stable. There's not a whole lot of iteration on top of it. And we Pythonize these functions or use C++ implementation to speed up the execution. And we were able to gain significant CPU instruction, to reduce the CPU instruction needs on that front. So that's part of controlling demand. Well, let's look at the second aspect of scaling up. Given certain CPU demand, how do we make each server execute more? Ideally, we want all the multi-cores on the server to be put to use, and we do that by running many worker processes in parallel that process user requests. But the number of processes is upper bounded by system memory. Let's take a look how the memory layout looks like. We run n parallel processes, where n is greater than the number of CPU cores on the system. Each process has two parts of memory, the shared part and the private part. Total system memory is made of this one shared memory and all the private memory added up together. So how can we reduce the amount of memory requirement so we can run more processes? Upon analyzing the memory configuration, we found that code itself is a big part of where our memory went. So the first things we did was to reduce the amount of code in memory. We started to run optimize, which may be obvious, but we were not running with -0. Now docstrings is gone from our memory. The second part is to remove dead code. We develop new features very rapidly, and there's a lot of legacy things that are not, despite the best effort from developers, there are going to be old code laying around. So with cProfile data, we were able to identify what are the code that's never get executed in our code base, and we're in the process of automating this code removal process. The second part is if we could move some of the private memory into shared area where only one copy is needed, then we would be able to reduce the total memory needs. Since configuration data is the same for all processes, it makes sense to move them to shared memory. So again, this is a bit of a trade-off. You can see between, if you put in the shared memory, then the access to the shared memory is going to be a bit more costly than if it's in a private memory. So you need some kind of metric to measure the trade-off, whether it makes sense for you to do that. The second part where we shared more is we actually disabled garbage collection for Python. This helped to prevent some code being moved to private part for GC purposes. It's not super intuitive, but so we have a great blog post on this, what we found. And Python community is actually looking into how it can make GC more effective without moving memory into private part. So with these memory changes, we were able to actually get more than 20% capacity increase because we increased the CPU instruction that we could execute on each server. Network can also negatively impact scale up of a server. Our Django processing model is synchronous. Each process can only serve one request at a time. So while it waits for external services to respond, it can cause server starvation and fewer CPU instructions get executed. As our application becomes more sophisticated, we are depending more and more on these external services, and this is becoming a bigger problem. One example is like this. On our home feed, We now have stories, feed, and sometimes even suggested users on the same screen. This has greatly increased the latency for home feed retrieval. However, we also found that these services are typically independent of each other. So instead of sequentially accessing these backend services, we explored using asynchronous I/O to access them simultaneously and greatly reducing the latency for this particular endpoint. Not only does it improve user experience, it also helps to mitigate server starvation problem and increase the capacity of the user. So conclude by optimizing memory and network access, we were able to make each server serve more CPUs. There's still work to do as well. Although Python and C++ were great, they're not as debugging friendly as Python. So we would like to find a generic, faster runtime solution for Python using JIT, for example, keeping the ease of programming and debugging, as well as the runtime efficiency. We're looking at asynchronous web framework so that we can remove more of our dependency and on the external services and improve the resilience. With newer Python version and better memory analysis tool, we also hope to gain more visibility into the memory utilization as we do with the CPU utilization, so we can further improve the memory footprint. And there are many other interesting opportunities that we're going to as well. Last but not least, scaling the dev team. So Instagram has an interesting combination of workforce. We have about 250 engineers, with 30% of them joined in the last 6 months. We have interns throughout the year who ship numerous features with us in their 3-month working at Instagram. We have Hackamenther from Facebook that works with us for 4 weeks on specific projects. And we have bootcampers who sign up for Instagram tasks that gets done in 2 days to 1 week. So as you can see, their familiarity with our system and the ramp-up time would vary, but not a lot. But we're shipping features rapidly. And each of these features would require some data to be stored somewhere, right? So when a product engineer starts to work on a feature, here are the questions that she needs to answer. As you can see, this is a pretty heavy process that each small feature has to go through. And we don't give people a lot of ramp-up time, like we said. As the team grows and the number of features grow rapidly, it is a big burden on the infrastructure engineers to babysit this process. And it's a slowdown for product engineers to deliver their feature. So what we really want is an architecture that would automatically handle caching, and that allows the developers to define relations and not worry about detailed implementations. It should be self-served by product engineers, and the infrastructure engineers would just worry about scaling this service. Turns out we have this infrastructure at Facebook called Tau. It's basically database plus write-through cache. It still uses a relational database, MySQL, as the backend storage devices, but it allows only very simplified data model. It's basically the nodes with objects and the edges with relationships. It may not be the most efficient as we used to have in terms of how you store the data, or you can't make direct sophisticated queries in the database itself. But it does the most basic things at very large scale. And this simplified data model allowed engineers to ship new features at a much faster speed without breaking things. This is just one of the examples where we'll continue to develop better data modeling and API to increase developer velocity. So where are these features getting developed? A typical source control at some companies with complex features will probably look like this. Right? Master will continue to contain incremental changes with smaller features perhaps, but branches are created to develop larger features, such as in our case, live or direct messaging. The problem with having the branches is that engineers need to be mindful of the code base they're working with and do mental context switching. There's branch management overhead. Surprises will arise when different teams work on different branches with overlapping code base. It makes it harder to do major upgrade or refactoring, like the data model simplification that we showed before. Performance data would be discovered much later in the development cycle and will be much harder to fix. So instead of branch management model for various features, we adopted the one master approach. With no branches, every diff needs to keep master working. So it's a continuous integration process. Engineers can collaborate much more easily. They don't have to think which repo or which branch a particular feature is being developed on. It's much easier to bisect problems and revert diffs when necessary. And we can continue to monitor performance for all features at the same time with pretty minimum overhead. But if every feature is being worked on in master, how do we ship the code? So we use gates to control who will be exposed to new features. Typically, at the beginning, only a few collaborators in engineering would be seeing the feature. And the dogfooters will test the feature still under active development, giving feedback so that the engineers can iterate on it. And then employees are the next victims before we develop this to the world. With this model, we know the feature works, but we don't know if it'll still work when 400 million people start to use it the next day. Sometimes between employee and the world, it takes 1 day to 1 week time. So we don't know whether the database can support the increased read-write RPS. We don't know whether Django has this much CPU capacity, and whether the network will become a bottleneck. So what we also do is load test. We make up artificial load that are semi-triggered by user requests. We would make assumptions about how many users would be using this feature, what type of load they would be generating. And we would exercise the backend infrastructure in this process. This helped us to prepare backend capacity to ensure a smooth launch of a new feature. So we're ready to launch. We need a release branch, right? Let's see. How often do we ship the code? Once a week? What do people think? Once a day? How about once a diff? So we continuously roll out our master repo whenever a diff is checked in. This results in about 40 to 40 rollouts a day. A typical commit will go out within an hour of landing in master. How do we make sure it doesn't all break loose, right? So code review unit test is very, very important. We're not perfect at unit testing, but we do our best. In one of our major recent upgrades, unit test was a great help in capturing majority of our use cases, and we were able to bring up the service right away. Once code is committed, it does another set of unit tests because I'll say diff on top of diff may not work. The next is production canary. Before the code is rolled out to the whole production tier, we actually run it on a few production servers and compare the exception rates and 500, 200 rates with the controlled tier. And if this canary tier is generating a higher than threshold failure, then we would stop rolling this out to the world. And finally, we roll it. But even despite this, a lot of tooling and canarying, we still might have problems in production. So extensive monitoring and alerting system helps us to discover problems fast. And sometimes we do need to revert. Okay, to wrap it up, we have covered 3 dimensions of scaling Instagram: scaling out, use more hardware; scaling up, use less hardware; and scale the dev team for velocity and productivity. Now, our Uncle experience is a little bit different now. But it's not all rosy. Scaling is continuous effort, right? There's no one endpoint where we say we're done. As you can see from my previous slides on the challenges and opportunities, we continue to tackle interesting scaling problems at the next level. Scaling is multidimensional. You want to look at different angles and make your servers all count. And scaling is everybody's responsibility, not just infrastructure and efficiency team. Now, we're not the policers, but we're the enablers, right? I think in some, I've got questions before, how do you make the rest of the team be more efficiency driven? I think, the deep belief in helping each other is really making a difference here. So, questions?
Okay, thank you very much. So we have 10 minutes for questions, if people have any. Oh, there's, I'm going to go back there.
Sorry, I'm just curious, could you tell us a little bit about where you do your feature load testing? Is it actually done in a production environment or non-production? Thank you.
Feature development does go to production, except it's gated and it's not exposed to the user. Is that your question? Load testing. Load testing. It's done in production.
Hi, thanks for the talk. With this volume of distributed continuous deployment, how do you conduct the acceptance test?
The canary?
Do you have a canary? Is the automation? Mm-hmm. Oh, thank you.
So we measure the rate of 500 versus 200 errors. And this is just one example. We have a number of metrics, both in terms of the error rate, the exception rate, in some cases even the CPU utilization, the requests to the backend. If your diff is generating a ton more requests to the backend than your control system, it could still be an indication of a bad diff.
And in this case, the text is no longer too much. Our test take half hour for every...
How long is the canary?
Yes.
It's not long. It's a couple minutes.
Minutes.
Because each server, they do serve quite a bit of traffic in here. We have to trade off between the time it takes to canary the diff and how we roll out the code fast. The faster you roll out the code, the more you can roll out, the easier it is to be able to identify which diff is actually causing the problem.
Thank you.
Excuse me, are there any downsides to everyone working on master, and how do you effectively gate the features as well?
I'm sorry, could you?
Sorry, yeah. Are there any downsides to all the developers working on master, and how do they sort of gate their features within that single branch?
I'm not sure. We have seen many downsides in terms of gating. There is a risk where, if you misconfigure, the feature could be prematurely exposed to the world, and it has happened, unfortunately. So, but when it happens, we develop better tools. We also canary the gates as well. Yeah.
Okay, thank you.
Hi. So you're deploying into your live environment 40 to 60 times per day. So how long does it take to roll out a new version to all your live servers?
Do you mean between commits and rollout?
No, if you're just saying, okay, now deploy to all the servers, how long does it take?
Oh, how long does it take? Oh, okay, 10 minutes? Yeah,
How many servers is it?
about over 20,000.
Okay, thanks.
Hi. I was just wondering, could you talk a little bit about your training culture and how you bring on your new young engineers? You mentioned that there was quite a few new starters in the last 6 months.
Sorry, I didn't quite get the question.
Yeah, I was just wondering what the training culture is like. Is it just learn on the job with
Oh,
new
with the
people that
training
join?
like?
The training culture,
Oh.
yeah.
So Facebook engineers typically go through boot camp. So there we have training on basic Facebook infrastructure, software pieces and deployment and things like that. Instagram has its own boot camp courses. And then it's basically the POC, the point of contact for specific tasks. Those are for boot campers. For hackamonthers, people who have already worked at Facebook, Instagram for a while, then it's a lot easier to understand the rest of the architecture. Interns, obviously have longer time, so they typically have their mentors working closely with them. That helps a lot.
I had a question. The database rollback, like a database in Data Center 2, it has an issue, the master, you have to promote the
Yes.
slave. How quick is that?
We were able to promote a slave. When we were still managing Postgres, obviously from the last slides, we don't anymore. We did not do automatic master-slave promotion. So once we detect a master going down and we promote a slave, then it takes less than a minute to promote.
So during your data center, like where they do the storms, it's sort of fake, right? Because do they alert people that, hey, we're about to do this?
We don't do real cutoff. We do promote servers before we cut off, yes.
And what do you do now? It's just pure Cassandra?
So we use Tau, which is also a relational database. Again, it's like you say, it's not a real cutoff without warning. So you have masters with massive writes failures and things like that. That doesn't happen. And yeah, we do have also Cassandra replicas, and we need to prepare for the storm. Obviously, in a real disaster, people would be more forgiving if there are more massive writes failures. But in a normal case, we don't want to impact the user experience on a regular basis, right? So, other than the databases, almost everything else is automatic drain.
I had one more question, unless someone else. We have the computation. Can you just, because you're doing like basically picture conversions, right? That's what's taking the CPU most of the time, or?
Yeah.
Can you just delay it? Like, let's say I upload a photo, and your CPUs are bound. Can you just delay that computation so that my readers?
So the computation is not done at upload time. It's actually done at read time.
Any other questions? Okay.
I have another question.
Oh, sorry.
Hi. I'm wondering, in the very long term, is Instagram considering biting the bullet and converting its backends to use the same one as Facebook to deduplicate, infrastructure work and all that stuff?
Do you mean Python versus PHP?
Yeah, to use PHP, hack.
Yeah.
Kind of stuff.
So right now we don't have much incentive to do that. We have a lot of business logic built into the code base. Most of the backend access, for example, accessing Tau is already in C++. That is used by both PHP and Python. So yeah, so right now we don't have it. And using Thrift, you can use any, to access backend services, you can use Python or PHP, it doesn't really matter. Performance-wise, we are looking, we have just converted to Python 3, which gained us quite a few percentage of performance gain. As Python is being active developed, 3.6 versus 3.5 also has performance gain. We're also looking at, as I was saying, the runtime JIT optimization. that hopefully could give us more CPU efficiency.
Thank you.
I do actually also have a question. Part of it you already answered. You're using Python 3. I was also curious about your usage of Cython. Do you use it? Do you implement? Because you mentioned you also use C and C++. Do you actually implement stuff in C, C++, or do you use Cython to interface to existing libraries? And if you write new C, C++ code, what's, in your experience, the performance difference between plain C, C++, and Cython?
We use both, actually. So especially for the code that is shared to access backend by both the Facebook front end and our front end, we use C++ because that will go for both. But in many libraries that we use in Python itself, we use Cython to do it directly without using C++. In terms of performance, I'm not sure. I cannot give you a number. I don't think we have actually done like apple to apple comparison with the same module being implemented in C++ versus Cython.
Okay, great, thanks. In my experience, it's about 2% what I found.
Okay.
Thank you.
Okay, thank you very much.
Thank you.